I'm Dr. Sikha Bagui, presenting for our group at the University of West Florida in Florida, Pensacola, Florida, USA. So the title of my talk is Machine Learning Classification Using Motif-Based Graph Databases Created from the UWF-ZEEKDATA22. So the UWF-ZEEKDATA22, this is actually, give me 1 second. I need to figure out how to go to the next page. Okay, so the UWF-ZEEKDATA22 is actually a new data set that we created at the University of West Florida. And I'll give a little bit of background of why we created the data set first. And then we'll go into what we did in terms of how we used the graph databases to apply machine learning. So basically, why we created this new data set, network intrusion data set. So previous data sets that cannot be used to detect adversary behavior in leading up to an attack. Just give me 1 second. I'm having problems with adjusting my screen on my end. Okay. So previous data sets cannot be quickly upgraded to include new techniques. So basically the idea is in machine learning, we're generally dealing with data that is has been collected in the past. And one of the problems that we face is when new attacks come in, it gets very difficult to upgrade the data sets, or we don't really have a mechanism of upgrading the data sets for new attacks. And so hence we created this data set, which has all the modern techniques and attacks. So, so introducing the UWF-ZEEKDATA22, this is a comprehensive raw network data set based on the MITRE ATT&CK framework. So, what's unique about UWF-ZEEKDATA22? It is mapped based on using the MITRE adversarial attack techniques and common knowledge attack framework. So what is this framework? This framework is a new behavioral model consisting of techniques, and sub-techniques, which documents different kinds of adversarial behavior. This model was first created in September 2013. And we actually have developed tremendous growth since that time. So until April 2021, there have been 14 tactics recorded, 191 techniques recorded, and 358 sub-techniques in this new attack framework. Okay, so the tactics are, we have 14 tactics. So for example, we have tactic 1, tactic 2, tactic 3, and then we have a sub-technique under every tactic. But the uniqueness of this framework is that this sub-technique can be related to the first tactic, but can also be related to tactic 2. So it does not mean that the subcategory is only a subcategory one tactic, but it can also be a subcategory of another tactic. And then we have sub-techniques under the techniques, and this sub-techniques can also belong to multiple tactics. So that's the uniqueness of this attack framework. So this MITRE ATT&CK framework reflects various phases of an adversary's life cycle and represents the adversary's goals for an attack. The attack tactics and techniques have many sub-techniques, which also have many other sub-techniques. And the sub-techniques are usually used for many different actions. So the different kind of attack tactics that we have are reconnaissance, discovery, credential access, privilege escalation, exfiltration, and so forth. And there are 14 of these. Once again, if you want to look at where the data is available at datasets.uwf.edu. Okay, so how we created the data, I just want to give you a little bit of background on how we created the data using the cyber range. And so here we have the cyber range architecture, which is pretty complicated to look at in this manner. But basically the part on the left, I'm not sure if you're able to see my cursor moving, So the part on the left, middle and left side of the screen is the different network, the network architecture, and on the right side of the screen is basically the big data or the Hadoop protocol. Okay, so the UWF cyber range consists of one vCenter server appliance and three EXXI servers. The cyber range allows for malware analysis of offensive cyber operations, defensive cyber operations in the safety of a sandbox. And the software stack consists of virtualization, router, and firewall techniques. UWF Cyber Range contains the VMware Center, pfSense, Kali, WebGoat, etc. Okay, so the cyber range consists of one name node and 5 worker nodes. This is actually the Hadoop cluster consists of one name node and 5 worker nodes. And it is designed to scale up from single servers to thousands of machines, each offering local computation and storage. And the cluster is designed to detect and handle failures at the application layer. Okay, so the Hadoop cluster basically has a Red Hat Enterprise Linux framework with Podman installed and Apache HDFS. Okay, so the data available at datasets is collected from Zeek log data, and it is being collected since 2022. Zeek in many ways exceeds the capabilities of other networking monitoring tools and is also highly customizable. Zeek produces an extensive set of logs that describes the network activities, and these logs not only document every connection, but also document application layer transcripts like DNS requests and replies. Okay, so the reconnaissance tactics. The reason I put the reconnaissance tactic up here is because our future work is mainly based on the reconnaissance tactics. The reconnaissance tactics covers network attacks that are carried out on the goal of gathering information to plan future attacks. There are over 9 million instances of reconnaissance activity in this data set. Okay, so the data set that we have was created mainly for reconnaissance activities and mainly using Zeek data. Okay, was mainly collected using Zeek data. Okay, so the first step was pre-processing. And so the idea that we are trying to do here is we are trying to take the data set and create a graph database, and based on the graph database, do machine learning. Basically, the idea is that we have too much data because we have big data. And so how do we make this data, how do we find ways to make it more efficient? So one of the ways of making it more efficient was to use graph databases. And since the idea on graph databases and in the graph motifs is to see where the attacks are originating from and where they're going, the attributes used in the graph formation were the source and destination IP addresses, bytes transferred, and connection duration. So additional attributes were derived from the aggregated attributes, which were count, average duration, and average bytes. So we pre-processed the data. We originally had 22 attributes, and of the 22 attributes, the attributes that we focused were source and destination IP addresses, which were used as the key and transfer bytes, and connection duration were aggregated. So the first table shows some sample input data, and the second table shows some examples of aggregation. Okay, so the only attributes that were used were basically source, destination, and a few features that were derived from the source and destination transfer bytes and connection duration, which were count, average duration, and average bytes. So the graph data sets generated, the data matching the star and cliff motifs were extracted, and a third data set was created with non-attack edges. So basically, we created a graph data set with attack edges, okay, and a data set with non-attack edges. And of the attack edges, we created two data sets, one called star edges and one called click edges. Okay, so the data set was complete of all the reconnaissance and non-attack connections that occurred irrespective of the motifs. And the clicks only made 18 rows, so we eventually eliminated the clicks. Okay, so the dataset schema, I think I'll go here. So the dataset schema, so we ended up with the ID, the from IP address, the to IP address, the count of the occurrences of the edges between the source and the destination paired vertex, the average duration, the total duration, the average bytes, which is the bytes transferred in all edge occurrences between the source and destination vertex pairs, and then the total bytes, and then we had the hop count, and then the tactic. Okay. Okay, so a little bit about the motifs. So basically, when we work with graph databases, there are several different kind of motifs. So the motif that we focused our work on was the star motif. Okay, which is, as you can see, is a picture like a star. So you would have like a source destination. This would be the source destination, and then attacks coming out of the source destination, and trying to figure out how many or which attacks are coming out of the source destination. So that's that. So the main focus was on the star motif. So the motifs are utilized to help understand the function and the structure of a complex network. And graph motifs are recurring subgraph patterns between vertices found in the complex graph networks. By understanding these patterns, one can learn valuable information about the dynamics of complex systems and can use the information to curate more effective strategies for network control and network analysis. In this research, two motifs were explored, the star motif and the click motif. Okay, so this is an example of the star motif. Okay, so here the central vertex is this IP address, and this is connected to these other IP addresses, and this means that the central vertex, this is generating or sending out attacks to other vertices. Okay, so this is an example of the reconnaissance attack. So this was an example of a generic star motif. We were giving an example of how a generic star motif would look, and this gives an example of the motif for the star motif for our reconnaissance data. Okay, so we have the central IP address and all these IP addresses that it's hopping to or going to in the star motif. Okay, so this is the example of our physical network data in the reconnaissance data. Okay, so then we have the click motif. Okay, the click motif are basically subgraphs, which shows different subgraphs or different regions that the graphs connect to. So in the click motif, you would have a vertex, but then it could also lead over there, which could lead to some other place, and that could lead to some other place, and that could lead to some other place. So it basically shows where the subgraphs are going to. Okay, so in our attack data, an example of a click motif in our attack data. So the yellow highlighted click motifs consists of vertices, and then of these vertices, and the blue highlighted click motif consists of these vertices. But this is how the click motif is behaving with our reconnaissance data. Okay, so machine learning classification results. Okay, so what we did was we pre-processed the data into the attributes that were discussed, and we ran the Bayesian classification, decision tree, support vector machine, naive Bayes, logistic regression, and SVM. And so the naive Bayes results for the star edges dataset. So the star edges dataset means the one that has the central vertex going out to the different places. Okay, so predicting reconnaissance using the naive Bayes classification results. Okay, so for these results, what we actually did was we ran using the same attributes over and over until we basically started off with one attribute, and then we added another attribute, and then we added another attribute, and added another attribute, and went so forth. And we ran it recurrently to see which ones would give us the best results. Okay, and here we only pulled out the best results, obviously. So the features that resulted in the best statistical matrices for the star edges using the Bayesian classification is the one that has the from attribute and as well as the average duration. The next, the next time I saw the almost similar. I mean, all of these results are almost similar. There's the from with the average duration, from with the average duration and hop count, from with the total duration, from with the total duration and average byte. But one of the things that is kind of consistent and recurrent in all of these attributes is the from attribute. So the origination IP address apparently was the most important thing in this star edges data set trying to detect reconnaissance. Okay, so what, just for interest's sake, we showed the best results. We also showed what is giving us the lowest results using the naive Bayes classification. So if we use only from, that gives us a very low result. The reason we did this is because over here it seems like from runs across the whole attribute list. So we thought if we just from, then it gives us a very low accuracy. If we run it with any other feature except total duration and total bytes, then it's also giving us a very low classification. So this was just done to see which features were actually performing the best. Okay, so now these results were for the star edges. The next set of results is for the non-attack edges. So for the non-attack edges, for the reconnaissance, even if the non-attack edges were mixed in, which means there's reconnaissance data, which is the attack data, and there's also benign data, which is the non-attack data. So if non-attack data is mixed in with reconnaissance data, then the combination of the from and the count features resulted in the best accuracy and the fewest number of features. Adding additional features to the from and the count kept the accuracy of the other matrices the same. Okay, so this was pretty much with mixing in the non-attack edges. So even mixing in the non-attack edges, the accuracy was pretty high. Okay, so the non-attack edges with the lowest results were the results with the hop count, which showed up as pretty low. Okay, so then the decision tree results for the star edges, predicting the decision tree with the best accuracy. The from feature was the only feature that was needed for 100% accuracy. So in this case, in the decision tree, the from feature was the only one that was needed. Adding additional features did not increase or decrease the accuracy. Okay, and the confusion matrix showed that there were no false positives or false negatives. Now, the difference in the magnitude of the decision tree and the naive Bayes confusion matrices is due to the differences in the training and validation sizes. There were 83 to 17% split in the decision tree compared to the 70-30% split for the naive Bayes and other machine learning algorithms. Okay, so for the star edges, the lowest results on the decision tree were using the 2 feature, which is the destination IP address. So the 2 feature, including the 2 feature without the from feature, resulted in the lowest accuracy. Okay, the decision tree for the non-attack edges, that is when benign data is mixed in, also came to pretty high results when with average duration and hop count. So the combination of average duration and hop count resulted in the best accuracy with the fewest number of features. Okay. Okay, the 2 feature resulted in the lowest accuracy with the hop count. Okay, for SVM, we found that there were over 30 combination of features that allowed for an accuracy of 100%. Okay, so that was just too many to list. So we just listed the from and the to, which in this case, the from IP and the to IP, destination IP, source IP and destination IP, as well as 30 other features were giving us very good results. The minimum number of features required to reach an accuracy of 1 was 2, which was the from and the to, that is the source IP and the destination IP. Okay, 2 unique feature combination resulted in an accuracy of 1, and below is a truncated table of the results. Okay, so the decision tree with the non-attack edges mixed in. Okay, with the non-attacked edges mixed in, we have the best results were by using the average bytes and the total bytes, which gave us an accuracy of 98.1%, and so forth. You see we have from and total bytes here, and you'll see that there's a consistent pattern of the results going slightly down when the non-attack edges are mixed into the reconnaissance data. Okay. The decision tree lowest results, the lowest results table was presented for SVM, since most of the SVM results were higher than the average. Okay, so okay, I think I mixed up the presentation of the SVM results. Okay, the logistic regression results. Okay, the source IP was the only feature needed for 100% accuracy in this model, and adding additional features did not increase or decrease the IP of the logistic regression results. Okay, so conclusion, the objectives of this research was to create machine learning models capable of detecting reconnaissance network attacks using the graph data from Zeek Connection Logs, and train the model with various network motif data sets from a graph database. And the final conclusion was, upon completion of this result, it was concluded that the most important features for predicting reconnaissance network attacks within the Zeek Connection Log dataset was the from feature, the source IP, which represented the network address from where the connection was originating. It was found that irrespective of which motif was used to train the model, the decision tree algorithm performed the best. And these findings provide valuable insights for future research in applying graph database to machine learners, for machine learners to create models capable of predicting nefarious network attacks. Okay, next, the references. The grant is supported by the National Security Agency in the United States.